we'll just go ahead and get started. So our speaker today is Stephen Kane, who is a full professor of astronomy and planetary astrophysics at the University of California, Riverside, in the Department of Physics and Astronomy, and he specializes in exoplanetary science. Stephen got his PhD at the University of Tasmania, later had postdoctoral appointments at the University of St. Andrews and the University of Florida. His research focuses on detection, characterization, and habitability of exoplanets using ground and space-based telescope facilities. Stephen is also a co-I for the Da Vinci mission to Venus, where he serves as the Exoplanetary Connections Lead.
Thank you very much. And thank you all for joining us on that wild ride of images up. So, all right, let's get started. This talk is going to be quite different, I have to say, from any other talk I've given. I thought a lot about what to say to you all, and I know most of you here. Some of you I know very well, and you've known me for many years, and so you know many of the things that I've worked on. It has been an interesting journey getting to where we are about connecting exoplanets to Venus. And so what I thought I would do today, if you'll humor me in this, is I'll give you somewhat of a personal perspective of that journey, because I'm a person who strongly believes that we forget the past at our peril, but I think it'll be interesting to see how all the dots were connected. And so I'll only be talking about my work really that does connect to Venus, but it is has this endpoint of what I do say at the beginning of planetary habitability anchor points, which is what I've been thinking a lot about over the last couple of years. And of course, a nice tip of the hat to Dr. Strangelove. I'm sure he's riding the Da Vinci probe down into the atmosphere of Venus. So getting started, this is a relatively up-to-date cumulative histogram of exoplanets that have been discovered. And one of the interesting things for me has been that I started grad school here in 1996, when we knew of less than one hand. It was like 51 peg. And at that time, we were debating about whether those radial velocity signatures were stellar activity at the papers by David Gray and so on that were really discussing this. And so I did grad school at nearby at the Space Telescope Science Institute. I was there for 3 years as an international scholar. And so we had just started really talking about this whole topic of exoplanets. And as you can see, radial velocities, it's been fairly linear in its discovery space, but transit has rapidly taken over, and we've crossed a significant threshold recently, whereas in the beginning that we were talking about giant planets and primarily from indirect methods. Now we have more than 5,000 planets, and there's a great deal of diversity among the different kinds of planets that were found. This is stuff that you've all heard recently. And it's really interesting to see that we are on this threshold of characterizing atmospheres, mostly through the transmission spectroscopy technique for transiting planets, at least in the short term. But we are thinking big from the Astro 2020 decadal about how we can go further towards reflectance and emission spectra. But there's a couple of things I wanted to say about this. First of all, something I've been thinking a lot about lately in how we got to this point of studying exoplanetary atmospheres is that the exoplanet community, and I'll talk more about this in a moment, it gets us as far as the planetary atmosphere depicted here. But the interpretation, it's been really interesting to me to see that we're finally almost forcing an integration of different fields and bringing multiple disciplines to the table. Because if I show my exoplanet spectrum to another astronomer, they'll go, oh, that's really cool, but I don't know what it means. And so, well, we really need to integrate more with biologists, climate scientists, geophysicists, planetary scientists, and many other disciplines who can really tell us about what all of this means. So that's a quick summary of where we're at the moment. So let me just step you through what has happened in the context of Venus through this whole journey and why I think it's so significant. So as I mentioned, I started grad school in 1996, and I was working not far from here. When I started, I was working on microlensing back in my dark past, often referred to as the black sheep of the exoplanet detection family, because only a few people understand it, and the black box data goes in and planet discoveries come out. But I was working on that because I was part of a microlensing network of telescopes, one of which was at the University of Tasmania, which is where my actual degree came from, even though I did much of my research here. When I finished that, as Erica mentioned, I moved to the University of St Andrews in Scotland, and that's where I started working on the transit method. Now, 2001, as those exoplanet people in the room will know, that was a significant time, because that was soon after the discovery that a known planet, HD 209-458b, transited its star. It was in a 3.5-day period orbit. And that, in my opinion, was one of those pebbles thrown into the stream that actually significantly diverted the course of the stream in the way in which we approach exoplanets. And when I was there, I was building instruments, and I built a facility called SuperWASP, and we deployed that in the Canary Islands, and that has discovered many planets from the ground. So after that, I moved to University of Florida, and there I started working on radial velocities, and added that to my. I felt a little bit like Pokemon for a while, that I was trying to collect all these detection methods. But at this, so up until this point, I was purely focusing on exoplanet detection, trying to understand the different techniques and what they brought to the table. And here's what I quickly realized is that although it's can be assumed that exoplanetary science and planetary science is the same thing, that's really not true. Because in all these methods that I've been talking about, as I mentioned, these are indirect methods. And so what the exoplanet community were doing, particularly in the early days, when it was at the high mass end, back in the 90s, it was all about, is this a planet or is this a star? And so what we do primarily in these exoplanets is we study the star extremely carefully and try to convince ourselves and the referee that the unseen companion we've detected is not a star. And we spent a lot of time on that in the 90s and 2000s of trying to perfect that art of trying to say what the object was not. Therefore, it is a planet. And these techniques had gone way back. I mean, essentially, the radial velocity method and the transit method is eclipsing binary stars, which we've been doing for 100 years or so. And we're just applying it to larger mass ratios and size ratios. So when we look at the exoplanet discoveries that are made, and so this is an artist's depiction of the Gliese 581 system. And once again, if there are exoplanet people in the room, then you may remember the nefarious nature of that. Some of the planets were, say, removed, and we had a lot of beautiful images like this. But one thing I always explain to my planetary science colleagues is because often the disconnect between exoplanets and planetary science is poorly understood, particularly from the planetary science side, as to why they can't just go to an exoplanet and start having a detailed conversation about geophysics in the atmosphere. And they have to remember that they're not talking to a planetary science, they're talking to a stellar astronomer, and to an astronomer, a planet looks like this. It's like the old meme about a spherical cow, basically. You know, it's an object of mass and radius, and oh look, the bulk density, and then that's kind of where it's left. And the problem I had when I was finishing at University of Florida is that I realized that this was going to come back to bite us as a community, because what I was seeing, especially during the 2000s, was that we were discovering smaller and smaller and smaller planets. We started talking about stars and brown dwarfs and where that limit might be, but we were finding smaller things, and we were trying to say quantitative things about it with almost zero expertise within the exoplanet field. And I knew that this was a wall that we were going to crash through, and it was going to be terrible eventually. So I started thinking about that a lot, and I thought about that around the time that I moved to the NASA Exoplanet Science Institute, which was in 2008. And 2008, I started working on a bunch of different things at that point. I started thinking a lot about the Hubble zone and calculating the Hubble zone. This was before Ravi's paper had come out, and so I was using Jim Casting's work, of course, but also Norman Sleep and others who have tried to fit polynomials to it and that sort of thing. I was thinking about planetary orbits a lot more from the radial velocity work and predicting times. I was looking at phase variations of planets and trying to use that to study their atmospheres. And I also started to think about Venus at this point. Now, the reason I started to think about Venus then is because of a couple of things, the significant things that happened around that time. Prior to the launch of the Kepler mission, there was a significant discovery that was made by Charbonneau collaborators from MERV. They were doing a ground-based transit survey of M dwarfs. And they discovered this planet GJ1214b, which was one of the smallest planets that had been found at that time. It was a big deal. And there was a follow-up paper that was written, a great paper by Leslie Rogers and Sarah Seeger. I really recommend people check this out, because it's a great detective story of trying to use what little we know about this planet as to what its nature might actually be. And so they were looking at all the different possibilities for each stage of the formation process. And they started out with the primordial materials, the gas formation process, initial gas composition, and then they end up with these three separate cases. And these three cases are quite different from each other, depending on the formation process. And remember, this is all consistent with the observations. That in case one, you have a mini Neptune, so a gas-dominated planet, or at the other end, you could have a planet that's dominated more of a rocky planet that has produced a substantial atmosphere throughout gassing, or some case in between where you add a lot more volatiles to create a consistency with what was measured for the bulk density. Part of the problem here, of course, is that this was in a size regime for which we have no analog in the solar system between the size of Earth, 1 Earth radius, and Neptune, 3.9. And so this was lying fairly much in between, and there was this enormous degeneracy. And it really started to emphasize the problem to me about how are we going to actually be able to say things about these planets that we're discovering using the transit method. And so then along came Kepler. So Kepler was launched in 2009, and Kepler was, at least initially, a statistical mission. Because one of the things I was saying to Ravi the other day, when I was at Space Telescope, we had one of the very first exoplanet meetings at Space Telescope in 1996. And at that meeting, NASA had some roadmaps. So they had some books, which I've still got a copy of, called TOPS, towards other planetary systems. And in there, they had a roadmap for the next 20 years. And what's really interesting is that transits is not mentioned in there at all. It was all radial velocities, direct imaging, and microlensing. And microlensing was the statistical pathway towards justifying direct imaging. So it's not that people didn't know about the transit method. Like I said, eclipsing binaries have been studied for more than 100 years. It's just that people didn't like the idea of this extremely low probability. This is a plot from a paper I published in 2008. And its transit probability is a function of orbital period. And what's overplotted on there are many of the known exoplanets. Part of the reason that they don't fall exactly on that line is, this was kind of the point of that paper, is because of their orbital eccentricity, which changes the transit probability slightly. But it shows this 1 over x, or rather 1 over a, dependence of the transit probability by the time you get to Earth. It's 0.5%. But the reason why Kepler was a statistical mission is because it uses a brute force approach. Okay, so if you've only got 1% chance of seeing a particular planet, then let's just look at 100 stars and we'll see one. Now we'll look at 100,000 stars and find 100 planets. That's the way that it works. But because the transit probability is very biased towards shorter orbital periods, when the Kepler mission was publicized, which it had been for the 10 years or so beforehand at various meetings, it was all about finding E to Earth, or finding the frequency of Earth-sized planets around these stars. But because of the short orbital period, I realized this isn't an Earth finding mission. This is a Venus finding mission, because that's what it's biased towards. So what this is going to do a much better job of is finding planets that are the size of the Earth, closer to their star, which means Venus. And so indeed, the results from the Kepler mission look something like this. So this is a plot that I show partially to antagonize some people, because you might notice I've essentially replaced Earth everywhere with Venus, but without changing the information, right? Because it means exactly the same thing. But it's really showing the distribution of Venus analogs as we get down into this small size regime. And one of them, I would say, personally, I would say the main result of the Kepler mission is showing that size increases, the size distribution increases towards smaller planets, which is something that we've long suspected that we've quantified. So the Venus mission, Venus mission, it is a Venus mission. The Kepler mission did have a lot of interesting individual discoveries which came out of it. One of which is Kepler 186, Elise's planet. And are we allowed to call it that? So I think that this is still the most important habitable zone planet discovery from the Kepler mission. The size of the planet is only about 10% larger than the Earth. Around an M dwarf. And so that was a really exciting discovery to come out of it. And remember, one of the, and this is a key point, which is that, as I said, the focus of the Kepler mission was about finding Earth-sized planets in the habitable zone. And so I found that in the early stages, when I interacted with the Kepler mission, and particularly the press officer of the Kepler mission, if I said anything about Venus, they weren't particularly interested. Said, could it have life on it? No. Okay, well, so there was a great emphasis on that. And one of the ways in which that became very clear, and I spoke with Tom a lot about this at the time, was that not long after that, Tom published this paper, a super Earth-sized planet orbiting in or near the habitable zone around a sun-like star. That is a wordy title. Too many hyphens.
It's a title by committee.
Yeah, and we did talk about that at the time, and about the discussion of this planet in relation to the Hubble zone. And it doesn't mention Venus here, at least in the abstract, but it does say this is the smallest planet, represents an important step on the path to finding the first true Earth analog. Now, as I said, I spoke to Tom a lot about that. We spoke a lot about the orbital parameters because I wanted to investigate this further because I thought that there was even more to this planet. And so this is what the system looks like, a top-down view of the system. So we've got a B planet in there, and this is the planet we're talking about, the C planet, which, as Tom had said in his title, it's like in or near the inner edge of the Hubble zone. But actually, we had another look at the orbital parameters and teased out things to do with the eccentricity and so on. And when we spoke about it further and I looked at the insolation flux, I realized that this was actually a pretty good Venus analog, or one of the closest that we had at that time. And so we ended up publishing a follow-up paper the following year, which we called A Potential Super Venus in the Kepler-69 system. And in that, we looked more at the orbit and we discussed, and this was one of the first, if not the first, papers that really spoke about this whole issue of what about the potential Venuses that could be present in these data. You can see it's a 1.7 Earth radius planet, which is why we call it a super Venus. Other than that, I will tell you that at that time, I had no idea what I meant by super Venus. Like just Venus, but more of it, you know, something like that. But I mean, we did identify that it receives almost exactly the amount of flux that Venus receives from the sun. What did that mean for the atmosphere? At that time, we didn't really have the tools, or at least I didn't have the tools to understand that properly. And certainly there are other people in this room who could talk more specifically to that. But as I said, the interesting thing about this, when I was, this is just a plot showing how we might learn more about the planet. And this is, as I mentioned earlier, I was looking at phase variations. And so the change in brightness of the star and planet combination as the planet is orbiting. And I suggested that as one way in which you'll at least might be able to determine that it had a relatively high albedo. And this is a Kepler planet, which means the star is faint, it wasn't easy to get a mass, and we're largely constrained to the precision of the photometry that we have, which is why I proposed that. But when I spoke to the press office about publicizing this, because I really did want to get the word out about the potential for Venus analog discovery, once again I got some pushback about, well, I mean, you know, it's not a, but eventually we did cross that bridge, because I kind of ranted at them a bit about this is so important for planetary evolution and, you know, analog stuff. And we produced a picture for the press release, this picture right here, which I love this picture very much. And apparently so do many others, because I see it all the time. It gets used in many other press releases. For example, it appears in the logo for, there's a meeting about a month from now, Ancient Venus, where the kind of flipped this way and flipped this way. So that did get some attention at the time, but I wanted to keep pushing forward. And so at that time, soon after that, I moved to San Francisco State University in 2013. And when I moved to SF State, I started working on other things as well. I added direct imaging to my collection of detection techniques. I started thinking a lot more about orbital dynamics. But significantly, I also started thinking a lot about occurrence rates and this thing called the Venus zone. And let me tell you what that means. This was actually a really interesting time, because what was going on in 2013 is that we were now after the end of the primary mission of Kepler. And so the dust was settling from, on this data set. And there were many people who were trying to look at this data set. Looking at the data set to answer the question that Kepler was specifically built to address. And that is, how many planets of the size of Earth are in the habitable zone? This was a very, very difficult question to answer, because what you had to do was you had to take raw distributions that look like this. So this is a size distribution of planets that were discovered from Kepler. And it looks like the most common planet in the universe is a sub-Neptune size, but of course, that's not true, because this is just raw numbers. What you're hitting over here is your detection limit. And so you had to be able to account for that. Trying to account for the detection limit and the observational bias in Kepler data was extremely non-trivial. And that was really amplified by when you saw the great diversity of numbers that different groups came up with. But this was the era of exoplanet occurrence rates. As I said, many, many teams were working on this. I've listed here some papers that I've looked at a lot over the years. But in fact, if you go to the NASA Exoplanet Archive, they have a long list of papers that goes way off the page, because you can see that this starts most recent and gets to about 2019. They go way, way, way further back than that. But I will say that this list of papers is dealing with all occurrence rates, not just Kepler mission, radial velocity surveys, or anything that wants to study what the occurrence rates of different kinds of planets are. But many of the ones that are looking specifically at the Kepler data will try to produce plots that look like this, where you set up a grid, as you can see, not linear, because the way in which we're approaching the period space means that we want to have it on some kind of a quasi-logarithmic space. There was one of the SAGs was set up to come up with these numbers. And same with radius, and then you end up with these color-coded things, which is essentially the percentage of stars that have a planet of that radius and that period. But like I said, these were all designed to address this primary question of either Earth, and that is Earth-sized planets which are in the habitable zone. It's not that I didn't care about that, but I was far more interested in where the Venuses were. And so that's when I started working with Ravi and Sean on this concept of the Venus zone, so that we could start to calculate occurrence rates within that region. So this is a figure that we produced at the time with the boundaries of the Venus zone from the conservative inner boundary, or the runaway greenhouse boundary, all the way to some high flux regime based on a thing that you may have heard of called the cosmic shoreline, which is a Kevin Zarmi and David Catling construct empirically relating atmospheric loss to what we observe from the solar system, and calculating how many terrestrial planets might fall in that regime. And what we found for solar type stars is it's almost half. And so this is implying that there's probably a lot of Venus analogs out there. And we were also able to feel more confident in these numbers than the other studies, because we had so many more planets in our data from which to calculate these occurrence rates. But I was unhappy because at that time, because I was still in the same boat as many of my exoplanet detection colleagues, which is that I was talking about planets and I had no idea what was actually going on. I could calculate a radius, a mass, an insolation flux, and that was it. I became increasingly frustrated that I didn't have enough background knowledge regarding planetary atmospheres to really talk about this in detail. And one of the papers which really drove this home for me was a paper by Mike Wade, a very well-known paper now that was published in 2016. And that's where Mike was applying GCMs to the case of early Venus. And by early Venus, I mean, say, about 1 to 2 gigayears ago, and showing that if he starts with temperate Earth-like conditions, that he can actually maintain those conditions, with a slow rotating planet by having substantial cloud formation at the substellar point, which serves to cool the planet, at least for that period of solar luminosity in the solar system history. And I was fascinated by this, both by the prospect that Venus may have had surface liquid water for a period of its history, but also that we could actually go there, that we could actually run simulations that would be able to comment on this. So as I said, I was extremely frustrated, and so I started to reach out for help. Now, at this point, I didn't really know anybody who was a hardcore Venus scientist. I didn't know anybody in the Venus community. So it turns out that there's an act. And so a lot of the folks in the exoplanet community are aware of exopag, but there's a lot of acts. And for the solar system, I think there's 8 acts. And there's one specifically for Venus, VEXAG. And so I reached out to VEXAG at the time, and I asked for their advice about attending meetings, who I could talk to, and just trying to draw some connections. One of the funny things about that interaction was that they interpreted my email somehow as an application to join the VEXAG steering committee, which is ironic. I'll come back to that later. But so they said, we've received your application to join the VEXAG steering committee. I said, oh, that's not what I was asking, but okay. And then they came back to me in a few weeks and said, your application has been denied because you don't know anything about this. So exoplanets doesn't count. So I was like, oh, okay, cool. But I did get advice from them about where to go, and so I went to the very next Venus meeting that was available, and it was this one, the Venus Modeling Workshop that was held at NASA Glenn in Cleveland. And it was one of the only meetings I've gone to where it was completely cold. I knew nobody at that meeting. I was giving a talk. I put in a talk about Venus analogs from Kepler data. But it was probably one of the most important meetings I've ever been to, because it really was that connection. I was like, so I always encourage people. There's a lot that's been said about the problem with silos that prevent interdisciplinary work. People tend to stay in their own field. But I really encourage people, if you are interested, to just try doing something like this. Go to a conference that interests you and see what happens. And for me, there was a lot that happened, and I met a lot of people. And particularly, I met these 3 people, Jada Nate, and Jim Head and Mike Wade. So all right. Okay.
Stop sharing.
Oh, it did?
Yeah.
Was that when the message came up?
It was right before the message. And it won't let us. See, people, this is why I'm a lab person. You're so wonderful. Yeah. Okay.
Thanks, Erica.
Please don't thank me. Probably the problem.
So, Jada and Jim and Mike have continued to be long-term collaborators with me on a variety of projects. So that was a really crucial time for me to be able to actually go and interact with Venus Science and see what was going on, because one of the things I definitely discovered at that meeting, it's hard to imagine now, but in 2016, the Venus community was exceptionally data starved. And so as a result, there were relatively few early career people there because it's Smithsonian to hire them. And they looked with great jealousy at their Mars colleagues who just seemed to get everything thrown at them. There were folks who were saying at that meeting, the reason Mars gets all the money is because of the connection to astrobiology and past life on Mars. So we need to make that connection on Venus. Let's talk about life in the clouds. And I said, no. The connection is actually that we're discovering many planets which are potential Venus analogs, but we don't know nearly enough about Venus in order to be able to characterize them. That's the connection. So my next big project came with Mike Way, where I was addressing one of the Kepler planets, Kepler 1649b. This was a planet which had been discovered with Isabel Angelo, and it was really interesting because this was one of the best Venus analogs that we had found from the Venus data. You can see that radius is similar to Earth and Venus. Incident flux about 2.3, so a little bit larger than Venus. And so what Mike and I had done is that we applied his rocky 3D simulations to this planet to show that just about every conceivable set of parameters for this planet starts to push it into a runaway greenhouse. And when I mean every conceivable thing, obviously we measure the radius, but we don't know the rotation period, we don't know the liquidity, we don't know the topography of the planet. And so we looked at many different scenarios. Every single scenario was pushed into a runaway greenhouse. And so we pushed that as potentially one of the first true Venus analogs that we had found. But then I moved to my current place, Riverside. I moved there 5 years ago this summer. And when I was there, I started to go deeper down the rabbit hole of this whole topic. I was really looking at the differences between Venus and Earth, but in the context of planetary habitability. And one of the key things that really pushed me down that path was a meeting I went to soon after I moved to Riverside in 2017, Habitable Worlds, and it was held in Laramie, Wyoming. And some of you were there. There was a lot of significant things that happened at that meeting. For example, that's where Thai originated from a lunch that was held there. But at that meeting, there was a climate scientist who I respect very much, named Francois Coget. And he gave a review talk. And in that talk, he said, if Venus did not exist in our solar system, we would not dare to imagine it. And I found that extremely profound because it's essentially, I interpret it as inviting you to do the thought experiment of, let's remove Venus, okay? It's not there. So we have Mercury, Earth, Mars, and so on. So if we did not have Venus, what would we think about planetary habitability? What would we assume? And it's when you start to go through that thought experiment, it's actually quite disconcerting, because you realize that there would be way more weight attributed to the size of the planet rather than many other properties as to whether it would retain long-term habitability. When I was thinking about this further, I would think about things like the fact that the atmospheric inventory of the solar system for terrestrial bodies, when you look at that, it's almost 98% of the atmospheric mass for terrestrial planets is contained at Venus, and yet we know almost nothing about it, about the evolution and the dynamics, especially the middle to deep atmosphere. And when I was thinking more about habitability factors, when we've thought about Venus in the past, of course we know that Venus is 30% close to the sun, receives twice insolation flux, which for a long time was a case of problem solved. That's why Venus is different from Earth. But of course, it has many other differences. Different rotation rate, different obliquity, and the surface subduction is in a very different state. The relative lack of magnetic field, the fact that it may not have had a substantial moon-forming impact early in its history, which would have changed its volatile inventory. There are many significant differences, and it wasn't clear to me which of if these were being weighted appropriately in how we treated the divergence of Venus and Earth. And so I sometimes think of it like this, where you have the same starting conditions for Venus and Earth, and then they're evolving in a similar kind of way, and then there's a divergence point. A divergence point, maybe, or multiple divergence points, but there may have been some significant event, for example, the loss of significant plate tectonics. and not being able to efficiently remove carbon from the atmosphere. Or there could be multiple outcomes, because the original dichotomy assumes that either you can store your carbon or you can't. Earth is a case where we can store our carbon, we can recycle it. And that is, by the way, one of the interesting things being in an Earth and Planetary Sciences department, I'm reminded of by my colleagues all the time, ever since I arrived there. You know, the interesting thing about Earth is that it's had surface liquid water for almost its whole history, which, you know, when I first heard that, I thought, yeah, well, yeah. But then you think about it, like, that's a narrow temperature range to have for more than 4 billion years. That's actually pretty freaking amazing. So, and so what are the conditions to that? If you understand the conditions to that, then maybe everything else will start to fall into place. And so that's the way I was thinking about this whole problem about whether we could have had an early Venus that may have had surface liquid water, and whether it would have been able to sustain that. But I started listing out the things that we don't understand about Venus. And of course, there's many, many things we don't understand about Venus. Things related to the interior and what the history of subduction has been. The composition, as I mentioned earlier, the composition and chemistry of the middle and deep atmosphere is very poorly understood. If it did have surface liquid water, where did it go? I mean, of course, it would have evaporated and ended up in the atmosphere, but then you've got this oxygenation problem. And so there's all kinds of questions about Venus that I realized were fundamental barriers in how we think about planetary habitability. And so by this stage, 2018, I was so obsessed with this topic because I had realized since that quote by Francois Forget that this wasn't just about finding analogs of Venus and analogs of things in our solar system. I realized that Venus was the key to everything, because Venus was showing us a completely different evolutionary pathway. And it was so critically important to understand it. So in 2018, a call came out from the National Academy of Sciences. We want your opinions on both the search for life and exoplanets. And I started to carpet bomb these solicitations. So I submitted one to each of those. So this is the very first one I wrote on the left. And as you can see, I'm starting to approve more and more people who are interested in this as well. And this was, of course, a precursor to the decadal. And so for the decadal, I did the same thing. There was one for planetary science and there was one for exoplanets. And really trying to build enough momentum that this would be taken seriously as a critical science objective from these decadals. And it seemed to have gained some traction, because what we saw in the Astro 2020 decadal, of course, the planetary science decadal had a lot that was said about Venus and whole chapters devoted to it. But what I wanted to make sure was that Venus was integrated into the Astro 2020 decadal, because I knew that's where the exoplanets would be. And indeed, Venus is mentioned multiple times in the 2020 decadal, and stated as being a local example of terrestrial planet evolution and a signpost with regards to the boundaries of habitability. So I was really pleased with that outcome, that we actually managed to get that written in to the decadal as a priority. I'll just quickly mention a couple of other projects I was doing in the meantime. One was looking at the orbital evolution of Venus. Venus has the smallest eccentricity of all planets in the solar system, 0.006 currently, compared to the eccentricity of Earth, which is 0.017. And I wanted to look at how that would have evolved in time, and in particular during the early stages of planet formation, if migration of Jupiter may have enhanced the eccentricity of Venus. And I found that it probably did. There are stable eccentricities for Venus, relatively high ones, that can be maintained, that has been exacerbated by the movement of Jupiter. How do you dissipate that much orbital energy? Well, through water loss, as it turns out, if you have significant amounts of water on an early Venus, then you can circularize the orbit relatively quickly. And another project which I published just very, very recently this year was looking at the effects of climate on a tidally locked planet, and arguing that Venus is our own local example of many of the exoplanets that we're so interested in, tidally locked planets. And what does that mean for the interaction of the atmosphere with the surface? Because what we've found from Venus is that that interaction is significant. The 90 bars of atmosphere and the evolution of that with the topography is changing the angular momentum of the planet itself. There is a transfer of angular momentum between the solid planet and the atmosphere, going backwards and forwards. And this is a big part of the reason why Venus isn't tidally locked, because that's an interesting question to ask. Why isn't Venus tidally locked? And a big part of the reason is because it's transferring energy with the atmosphere. And we see that in data from the Akatsuki mission, where we have gravity waves which are forming over the equatorial continent of Aphrodite Terra. This is a substantial thing to consider when we're thinking about tidally locked planets, because they may not be tidally locked due to similar reasons, depending on the state of their atmosphere. So anyway, I just want to quickly finish it up, because I know we're going over time, but I just want to say that there are a couple of important things that happened during this period as well. One is the launch of TESS. I was there, and Tom and Lisa, you were there as well, right? And so that's a picture of me at the launch of TESS, which happened about April 2018, I think. But I think last year is going to be remembered for many years to come as one of the greatest years for Venus. One of which, of course, is the selection of 2 Venus missions by NASA, Da Vinci and Veritas, and of course the European mission Envision as well. And so we've got this international fleet which is heading to Venus, and the combination of that with the outstanding success of the Webb launch. And it's been so successful that the lifetime of Webb is going to extend far beyond when these will be arriving at Venus later this decade. And so there'll be overlap there, which will be very nice, because it means that we can apply the science of Venus to Webb observations and target selection in real time. And so that overlap is going to be really, really important. I'll just quickly, actually I'll skip over that. I'll mention one of the other things that I've been doing is working on the transiting exoplanet survey satellite and for masses, measuring masses using an enormous amount of Keck time. The reason that I'm doing that is because those masses are going to be critically important for the transmission spectroscopy from their atmospheres, which is coming. I've been working with my grad student, Colby Osberg, on selecting targets, which would be the best targets for James Webb and atmospheric characterization. And so he has he published some early results on this in 2019, and he has a new catalog paper coming out soon, which will be talking more about which are the best targets for James Webb. But of course, we'll be able to distinguish between Venus and Earth analogs from James Webb. That's going to be really, really tough. We do, because one of the things to remember, of course, about transmission spectroscopy is that you're sampling the very top of the atmosphere. And from that, you are trying to infer some kind of a pressure temperature profile all the way down to the surface. There is an enormous amount of degeneracy that lies within that regime, and due in no small part that we don't even understand that for the nearest Earth sunspot. And so, of course, this is what the new missions, one of the many things that the new missions will be trying to address. And so we do have some great targets from Cycle 1, which are coming out. This is a transmission spectrum which was simulated by Colby, I think he's in PSG, for some of the targets which are going to be observed. And we've got a few favorites from Cycle 1, TRAPPIST-1c, Gliese 1132b, and L9859b. So those are coming in the very, very near future, but we're hoping for many, many more of these. But one thing to keep in mind is that, as I said, we'll be able to tell the difference between Earth and Venus. It's actually really hard from those altitudes, because the CO2 lines look actually really, really similar, especially if you get hazes which are truncated. And so that's going to be a real challenge. So I'm going to finish by saying, okay, honestly, like I said at the beginning, this is unlike any talk I've ever given. If this wasn't a giant ramble, I don't know what is. So what have we come away from this learning? Well, hopefully, if nothing else, I hope it's enlightened some of you as to this pathway, as we've meandered through, trying to understand what it is that we're actually doing with planet detection and what we can learn from that and how that relates to the solar system. But one of the things that I take away when I think back about what I've learned is that, first of all, as I said, terrestrial planets are extremely common. That's great news for all of us, whether you're interested in habitability or Venus analogs. But one of the things I often think about is that we will never have in situ data for an exoplanet. We're not sending a lander to Proxima Centauri b. We're not sending, an orbiter to TOI 700d or anything like that. We're not doing that. Maybe ever, right? So that means that whenever we're talking about planetary atmospheres, particularly in the context of inferring surface conditions, which I think is what the focus will often be on, then those are going to be based on models. And those models are based on the actual data that we have here from the solar system. So if we get it wrong here, we'll be catastrophically wrong there, but we won't even know. And so that's just a disconcerting thing to think about. And so Venus, as I said, I think it's a real anchor point for habitability because it's crucially important for showing the possible divergences. Did it ever have surface liquid water? I'm not sure. We can talk about that over a beer later. But whether it did or it didn't, it's still equally important because we have these two completely different outcomes for an Earth-sized planet, and I think that's crucial. Near-term opportunities, I mentioned JWST Cycle 1, lots of great targets coming from there. But as I mentioned, the absorption features in those pass bands are still a little bit ambiguous as to what they'll actually mean. It'd be a good first step to know that there's CO2, but what that means about surface conditions will be hard to say. Mid-term, of course, we've got our Venus missions, and that's going to be dramatically change, I believe, the way in which we approach the exoplanet data. And so it's great to have that overlap with James Webb. Longer term, how can we really solve this problem? Well, a couple of things. Direct imaging and getting reflecting spectrum might give us more wavelength coverage into regions, particularly the UV, if we see ozone absorption. And there are extra clues that will come into play there that I think will be really important. I know that Eddie Schweiderman is visiting later this year, so if you want to hear a lot about the UV coverage, he'll happily talk to you a lot about that. If we can get rotation rates, that'll be great. But of course, Venus has a super rotating atmosphere, and we can't see the sun. So that's going to be a real challenge as well. But I think we're having these extra pieces will give us a lot more confidence in our models. Anyway, I better stop there. Thanks everybody for hanging around. Yeah.
Thanks, Steve, for great journey into our Venus and Venuses. So that's basically the question. Is some of them are probably young Venuses, some of them are old Venuses, right? Some of them around M dwarfs, some of them around K dwarfs, and very, very few of them probably around G dwarfs, like us. So from that point of view, if the Venuses are old enough, then the atmospheric escape, especially around M dwarfs and K dwarfs, can remove a certain amount of atmosphere, making them thinner. So the question is that what would be the condition for the runaway greenhouse? I mean, in terms of atmospheric pressure, to transition into the runaway effect and expect the CO2, for the JWST observations.
So to be clear, are you talking about the removal of CO2 from the Venus?
Yeah, right.
Yeah, I thought about this, and it's something that I'm working on a lot this week. It's one of the main reasons I'm here to work with Ravi on a project I'm working on at the moment about whether Earth returning to Venus or Venus returning to Earth. When I think about this, I often think about that quote from the movie Spaceballs, where they accidentally set off the self-destruct mechanism at the end of the movie, and President Scrooge says you need to turn it off, but Colonel Sanders says it's irreversible, and the president says like my raincoat. So I always think about raincoats when I think about it. Anyway, removing CO2 from a CO2 dominated atmosphere is actually pretty hard. And there was a great paper by Xiongfei Dong that spoke about this in the context of some exoplanets, but he spoke about CO2 atmospheric erosion. And my understanding, if anybody in this room could correct me if I'm wrong, it will be you, but my understanding is that current atmospheric erosion from Earth is slightly greater than it is for Venus by a factor of about 50%. And so when I've looked at degassing models, because one of the things I'm working on at the moment is how would Earth degas and how much would it remove? If it's degassing primarily CO2, then that actually can hang around. And so then I tried to approach it from the opposite direction, which is, well, can we remove substantial CO2 from Venus? And you can't really during the main sequence lifetime of the star. And so once you end up with a CO2 dominated atmosphere, it just seems to stay there.
If you have like 1 bar atmosphere and a lot of XCV flux, like around 10 times at least greater than we have today, then the CO2 will be dissociated because you need only 5 electron volts of energy in order to create CO. So I'm saying that maybe you can have a lot of CO-rich atmosphere rather than the CO2.
I see what you're saying.
That's what I'm saying.
Yeah.
And then oxygen will escape through the ion escape, for instance. So that's the one possible scenario.
We may not even reach a CO2 atmosphere. Yes.
Yeah.
If you're in a runaway greenhouse state, you have a water vapor atmosphere. Then if you start evacuating, you have an oxygen dominated atmosphere mostly. And it's depending on what the planet is outgassing, you have oxygen and CO2.
Well, oxygen will ionize and then can escape through the ion escape.
So depending on the age of the system,
Yes, depending on the age of the system, exactly. Yeah. So the young businesses might be great examples too.
Yeah.
So you talked about the importance of the planets and clouds, reflective clouds, and a lot of these factors are driven by the water content in the interior and the outgassing. Right, the planets, obviously, lubrication is a major factor. So have you looked at, and now that you're delving into some of these interior processes and interior atmosphere, what if you had an exoplanet, the exovenus, with significantly more higher water fraction in the interior, but a similar, of course, evolution?
Yeah.
Could you maintain, or would it even be worse by driving up? I don't know. How does that? There's a lot of feedback factors that I don't.
I think that would be worse because I think by the time you degas substantial amount of the interior water, you would have already lost your surface water. And so if you lose your surface water, then the subduction of the surface is going to slow down. Not necessarily stop, which is one of the current things we're looking at for Venus, but the slow down substantially. And then everything just gets trapped in the atmosphere from the degassing. So I suspect that would be worse.
Okay. So you early on you had a picture of like a gray circle.
Yeah.
And you're like, astronomers, don't know a lot, but like that's actually as much as we know now about basically every single rocky planet. Right? We don't know any more than the gray circle, right? And may not for a while. Like even with James Webb, we may not learn anything more with just a gray sphere.
Yep.
So at what point are we going to be able to like use the information that we get from solar system planets and have the data from exoplanets to actually have those fields more closely defined?
Well, there's a couple things here. One of the so there's the interior and the atmosphere. There are people who think about the interior, like Kane and many others, about whether we can use proxies for stellar abundances. to improve first order estimates for what the interior models and core size of terrestrial planets may look like. But that is limited by how little we know about the terrestrial bodies in our solar system. Once again, it's kind of it's truncating it. So, like for example, for the Earth, many of the refractory elements like silicates and magnesiums are within about the same as solar abundance, but for giant planets like Jupiter, they're an order of magnitude off. So it'd be nice to know if that's also true of Venus, but we know so little about Venus's interior that we can't have good estimates of that. So that's one of the other reasons why we want to know more about the Venus interior. So that will help us with our interior models for the terrestrial planets. In terms of the atmospheres, yeah, this is where we're trying to improve the Venetian models, because the best model I would say right now, and Tamar's going to jump on me if I say the wrong thing here, but I think is LND for a Venetian type atmosphere, and so that's from Francois Poget's group. However, that's trying to recreate a present day Venetian atmosphere, which we do, but the full transition from a temperate into a modern Venus atmosphere is still extremely difficult. And part of the reason for that is because of the change in chemistry that occurs within different layers of the atmosphere once we exceed, say, about 10 miles. And so that's where we'll be really helpful with Dimensity to have a full chemistry profile of the middle and deep atmosphere. Will really help, I think, models like LND to be able to fully simulate not just the present states of different atmospheres, but the transitions between them, which I think is a crucial part of the model. Does that answer your question?
Yes, I'm curious, what delineates a Venus analog for you? I guess the difference between an Earth analog and a Venus analog is the temperature, but is there an upper limit? So like, oh, this is too hot to be a Venus, or is this? I mean, I guess size would be an obvious thing. Like, oh, it's too big to be Venus. But your plot sort of extended on to the inside, and I don't think included Mercury. But if we don't know, like, is Mercury a Venus analog until we know whether it has an atmosphere? Or
You want to show the Venus zone because that's where
yeah, what is a Venus zone? I'm curious about that.
that's the deification.
It seems a lot bigger than how this one.
It is.
Yeah, sorry.
Okay, almost there. Tick it out.
Here we go.
Yes.
So this, yeah, to be clear, this is the inner edge of the conservative hub zone as calculated by Ravi, but this is for a true Earth analog. And it's something to always keep in mind about the Hubble zone boundaries, is that it's taking Earth and changing the insulation flux and seeing how the radiation balance evolves. So if you have something which is larger or has different starting conditions, then you're going to start to diverge from that model. And it's not, I think it's one of the challenges that we would like to apply future GCMs to, of how that chemistry might change for something which is 50% larger than the slightly higher insulation flux. It would be nice to be able to do that, because the case where a bit later on, Kepler 1649b, where I did that, once again, that is assuming very Earth similar starting conditions.
So
Yes,
Yeah, I just want to point Vlad's point about the high energy flux is also a great one.
That's included in the spot actually. That's what Steve
Well,
that's
the
the inner-
losses, but imagine you have CO instead of CO2, that changes your atmospheric temperature.
No, this is for all the things. This is the straight vertical dashed line is the erosion boundary.
Erosion, but not chemistry. Where does your atmosphere transition from a CO2 dominated
That would
to
be
CO?
much more inside of this.
So I'm only saying there's another, it could be another
Yeah.
dimension,
No,
another regime,
That's our,
which is not Venus.
Yes,
It's
that's-
CO Venus.
right, that's our 2018 paper on the bonds.
Yeah.
Their dimension.
Well, it take higher, it take the.
Higher, that's a different chemical.
Yeah.
So the outside boundary is the edge of the habitable zone, basically, and the inner boundary is the, like, it gets.
yeah, that's the empirical.
So that's 25 times the stellar flux.
Oh, okay,
So Mercury is about 7 times, so Mercury is inside the Venus. So,
okay, okay.
but that's not a Venus-sized planet though.
Right.
So it's not, should not be there. So it's in there, but it should not. be.
Yeah, I understand.
And Mercury is a great mantle stripping analog, which that's a different conversation.
Yeah. And is there an upper temperature as well, or is it just flux?
It's the flux.
Okay, the flux.
I have those two phenomena. I have, left I start splitting and people start using equilibrium temperature because it's based on albedo calculations. Flux is
Yeah.
something that you can actually calculate from.
Yeah, sure, temperature.
From the measured stellar properties. So
But I imagine they still get a lot hotter than actual Venus. Yeah.
someone else raised. Then we get.
Could you comment? Are you using exoplanets to inform your understanding of Venus, or are you using your understanding of Venus to inform your understanding of exoplanets, or both?
Both.
Both. Is that
Yes, it's definitely a
more
two-way
one-
street.
More one than the other?
Well, so they're very different. Well, which is that the way I would put it is this: is that we're using Venus to gain an understanding of the evolution and atmospheric chemistry of individual exoplanets. But the way in which I see exoplanets is kind of like this statistical hammer. I mean, now in the regime of 5,000 plus, this is it will be telling us how commonly Venus analogs occur from a statistical point of view. Of course, there are individual exoplanetary systems which are interesting, and you can then go down the rabbit hole. But fundamentally, I see exoplanets as a giant statistical exercise to put our solar system in context. In this case, Venus, as a function of time. And so, one of the main challenges, and I think it's been broadly mentioned several times, that there's the axis of time. And we always think about, like, for example, if Mike Way is right, then it means if we looked at our solar system at 3 gigayears, then there's 2 Earth-sized planets with surface look what. That's quite a different situation. And so when we're looking at other planetary systems, trying to get a better handle on the age, I think is going to be really, really important to all of this. Because I mean, if you imagine that we looked at all the planetary systems we looked at were like 9 gigayears old, and it turns out that they all had runaway greenhouses, we'd say, oh, Venus is really common. But no, at 9 gigayears, yeah, maybe. But yeah, trying to get that axis of time sorted out, I think is going to be a big challenge for the statistical interpretations.
Yeah, I have a question about the interior structure of the evolution process. You mentioned in one of your slides, saying that the host planets, the Venus and Earth, starts from similar initial conditions and bifurcates here in the evolution time. Now, one question I have, is that what is the mechanism? What is the physics behind that makes Venus doesn't have an active plate tectonics on those skies? So, can you make a sort of comment?
Yeah. So Mike, yes, it's kind of what I hinted at, which is that either you can recycle your carbon or you can't. And so if Venus did have a temperate period, then my feeling is that it was the loss of significant surface subduction which caused the divergence. That's my feeling. Or you Martin Thibault recently published a great Nature paper where it was saying, well, actually clouds would have formed on the night side of the planet at the very start. You never get surface liquid water on the planet, in which case it's right down here at the bottom, which is mostly related to the insulation flux.
I think we are a bit over
Yes.
time, but let's
Thanks, everyone.
Thank you. Thank you, Mr. Walker.
Cool, good stuff, man. Always thought provoking.
Hey, was everything okay with you?
Yeah.
Obviously, you got
totally
back
fine.
okay. Yeah.
2 weeks later, my wife came down with
There
it.
is an,
Yeah.
And it was like way worse than me. So.
there are some.
Well, I